The final part of this chapter is going to be focusing about something known as the respiratory quotient, also referred to as the RQ. You must know the definition of RQ. They may ask this in the exam. There can be two definitions you can give in the exam, which means the mole of carbon dioxide produced during respiration divided by the mole of oxygen used up during respiration in a period of time. Or the second definition is the volume of CO2 produced during respiration divided by the volume of oxygen used up during respiration in a period of time. So, for example, let's look at the first definition, which is using the mole of CO2 produced divided by the mole of oxygen used up. So in the aerobic respiration of glucose, as you can see here, C6H12O6, which is glucose molecules, requires 6 oxygen molecules. And when it's broken down completely, it will produce 6 molecules of carbon dioxide and 6 molecules of water. You can represent the 6 oxygen, 6 carbon dioxide, and 6 H2O as moles as well, 6 moles. So the RQ of glucose equals to, remember, mole of carbon dioxide produced. And what was the mole of carbon dioxide produced in that case? It was 6. In that case, 6 moles of carbon dioxide. So, and then the mole of oxygen used up is basically 6 as well, based on the chemical equation, and therefore the RQ of glucose is 1.0. Quite simple that way. Let's take another one. What about aerobic respiration of fatty acids? C18H34O2 is a particular type of fatty acid, and it requires 25.5 molecules or moles of oxygen, and when it's broken down completely, it gives you 18 moles or 18 molecules of carbon dioxide and 17 moles of water. By the way, you do not need to memorize the chemical formula. They will usually give you the chemical formula, and they may just ask you to balance the chemical equation. Certain exam questions would do that. So the RQ of fatty acid in this case is 18 moles of carbon dioxide produced, so 18 is the numerator, and 25.5 moles of oxygen would be the denominator, and therefore 18 divided by 25.5 is around 0.7. Now, you do have to memorize the respiratory substrates and also their matching RQ values. Remember, when we studied the previous video, I told you that your cells can use carbohydrates, proteins, and lipids or fats as respiratory substrates. The RQ value of most carbohydrates will be around 1.0, proteins will be about 0.9, and lipids about 0.7. This needs to be memorized, especially carbohydrates and lipids. They love asking that in the exam too. I also want you to understand that we cannot calculate the RQ value for anaerobic respiration. For example, if you look at this anaerobic respiration in yeast, where the yeast breaks down the glucose without the presence of oxygen, it produces 2 molecules of carbon dioxide, so 2 will be the numerator, but did it use any oxygen? It didn't. So there are 0 moles of oxygen. So 2 may not be divided by 0. It is impossible in this case. That is why RQ, or the respiratory quotient, is only specifically used for aerobic respiration. Imagine for a second the person is standing on a treadmill. You know those treadmill are those stationary machines that people run on. It looks like a hamster wheel. Yeah. So imagine in this case here, the person has a mask attached to their face, and the mask is attached to a machine, and the machine is able to calculate the volume of CO2 the person produces and the volume of oxygen the person uses up. And the machine will then be able to immediately calculate the RQ value. And based on certain activities, a graph of RQ over time was plotted. So, for example, in this case over here, the person was asked to do 4 types of activity: stand on the treadmill, slow jog on the treadmill, walk on the treadmill, and sprint on the treadmill, and the machine would calculate the person's RQ value. in this case. And let's look at the changes of the RQ value. When the person was standing, the RQ value was 1, and when the person started to do a slow jog, the RQ value quickly decreased to 0.7. When the person was asked to walk, it switches back to 1.0. But when the person was asked to sprint, the RQ value suddenly started going up. So this is quite peculiar. Now you might be thinking, oh, I thought RQ values are only supposed to be between 1.0 and 0.7. Why is it suddenly going above 1.0? Well, let's talk about it. So in this case over here, when the person was standing, the cells were mostly using carbohydrates as a source of energy, because carbohydrates can be easily broken down like glucose and such. Now, but when the person was doing a slow jog, perhaps the muscles needed more energy, and the muscles switched the source of energy to lipids. So more fatty acids were broken down during respiration in that case. But when the person started to walk again, perhaps in that case, the body switched back to carbohydrates, because you do not need that much energy in that case. But the sprinting is the interesting one, because during sprinting, the RQ value goes above 1. Remember, RQ value is volume or mole of carbon dioxide produced divided by volume or mole of oxygen produced. So to have a very high RQ value, because the RQ value in this case is quite high, either the mole or volume of carbon dioxide increases, or the mole or volume of oxygen taken up decreases. So in this case, perhaps we can assume that the oxygen level used up is decreasing, because that's the relationship in mathematics, right? When the denominator decreases, the value increases. So why would the oxygen level decrease in this case? Perhaps in that situation, the person is doing more anaerobic respiration. There is a lack of oxygen used up. So while sprinting, the person switches to more anaerobic respiration, causing the RQ value to go up, reaching a limit that does not exist. So that is what we have to understand for this. Now let's look at a few experiments. Now the first experiment over here that we have to see is how to measure the RQ value. This is extremely important to know. So for the RQ value, we start off with germinating seeds. Germinating seeds are just seeds that are respiring, they are producing ATP, and they are growing. Okay, so the question over here is, what are they breaking down when they are growing? Are they breaking down carbohydrates as a source of energy, or are they breaking down lipids as a source of energy? You can't ask the seeds now, can you? So you will have to do an experiment. The experiment looks something like this. You put the seeds into like a chamber and you seal the chamber, but there is a capillary tube connected to the inside of the chamber, all right? And then after that, you also have soda lime or potassium hydroxide or sodium hydroxide, and the function of the soda lime, KOH or NaOH, is to absorb the CO2 in the chamber, so that inside the chamber only oxygen is present. I mean, oxygen and nitrogen will be present along with other, inert gases, but we don't care about the other gases. We are just focused on oxygen in this case. So there are no carbon dioxide molecules in there at all. And of course, in the capillary tube, we also put a liquid droplet. All right. Now, how does this experiment actually work? Now, let's represent the oxygen as those dots. Okay, you cannot see oxygen molecules, obviously, but I'm going to represent those dots as oxygen molecules, those small little dots inside the chamber. Now, as the seed starts using up oxygen, because the seed is carrying out aerobic respiration, so the seed will absorb the oxygen from the surrounding. So what happens to the volume of oxygen? It decreases. And as the amount of oxygen in the chamber decreases, what happens? The droplet starts moving towards the seeds, or it moves towards the left. The reason why is because as the amount of oxygen in the chamber decreases, the pressure also decreases in the chamber. It creates a suction effect, and that suction effect will pull the droplet inwards. So the movement of the droplet shows that oxygen is being used up. So you're like, oh, okay, that's good. But the question here is very important. How much oxygen, or what's the volume of oxygen that is being used up? because you can't see the oxygen. You could not count the oxygen molecules, could you? I mean, of course, in my diagram here, you can count the dots, but in reality, you can't do that, right? So how would we measure the volume of oxygen used up by the seeds? The answer is actually quite interesting. The first thing we do is we measure the distance the droplet moves. For example, over the course of the experiment, the droplet moves 5 millimeters, as an example, by the way. And what was the reason the droplet moved 5 millimeters? Because oxygen is used up. So that part where I've highlighted in pink is basically the volume of oxygen used up by the seeds. But how do we measure the volume of oxygen? The answer is very simple. You must know the radius of the tube, because the radius of the tube there, as I'm giving you, is 1 millimeter. This is just an example, 1 millimeter, and the distance the droplet moves was 5 millimeters, right? So how do you calculate the volume of a cylinder in that case? Pi r squared, r being the radius, times or multiplied by L, which is the distance the droplet moves. So pi r squared, which is pi 1 squared, multiplied by 5. And when it's multiplied by 5, in this case, it will give you 15.7 millimeter cube of oxygen was used up. That was the volume of oxygen the seed used up, by the way. So you're like, oh, okay, so the seed used up 15.7 millimeter cube of oxygen. That's fine. The problem is we now know the volume of oxygen used up, but we do not know the volume of carbon dioxide that was produced by the seeds. Why? Because whatever carbon dioxide that the seeds produced were absorbed by the soda lime. So, how do we find out the volume of CO2 produced? You have to repeat the experiment again, but in this case, you have to repeat the experiment without the soda lime, potassium hydroxide, or sodium hydroxide. Question is, why? So, let's look at this. Think about it logically. So, let's imagine that as the seed uses up oxygen, what happens to the liquid droplet? The liquid droplet moves to the left, as you can see over there. So that's fine. But now the seed, as it carries out aerobic respiration, it also produces carbon dioxide. Is the carbon dioxide going to be absorbed by anything? No. And that carbon dioxide will push the liquid droplet. So as it pushes the liquid droplet, it goes back to its original place. As you can see here, oxygen is being used up by the seed again, taken up by the seed again. The seed produces carbon dioxide. The carbon dioxide pushes the liquid droplet. Now, how do we calculate the volume of CO2 produced then? When you do the experiment, let's say at the end of this experiment, the liquid droplet only moved 0.3 millimeters. It only moved a net movement of 0.3 millimeters towards the seed. So, how do we calculate the volume of CO2? So in this case over here, with soda lime, the droplet moved 5 millimeters, correct? But without soda lime, the droplet only moved 0.3 millimeters. The reason was because it was being pushed by the CO2. So we can assume that 4.7 millimeters over there, 4.7 millimeter worth of CO2 was actually produced. Okay, so that is why the droplet did not move so much, because the CO2 was also pushing back against it. So in this case over here, what is the volume of CO2 produced? In this case, you basically do the formula, where the formula is pi r square times L, where pi r square is just basically pi is pi, obviously, right? R in this case is 1, and then times L, which is 4.7 millimeters. And in this case, it produces 14.8 millimeter cube of carbon dioxide. So in this case, we have the volume of CO2 produced, and we also have the volume of oxygen used up. Therefore, the respiratory quotient in this case is 14.8 divided by 15.7, which gives you an answer of 0.94. So you can assume that during this respiration, the seeds are using up proteins or carbohydrates as respiratory substrates because 0.94 falls between proteins and carbohydrate. Proteins were 0.9, carbohydrates 1.0, so we can assume that the seed was using a lot of carbohydrates or proteins that were being broken down to produce ATP as the seeds are growing. Okay, if you're not so sure, let's try another simple one in this case. Now, this simple one over here is with soda lime and without soda lime. All right, so in this situation over here, let's say with soda lime, on the one on the left, the liquid droplet moved 8 millimeters. All right, and the radius of the tube, as I'm circling over there, the radius is 0.3 millimeters right now. Okay, the radius will be given in the exam, do not worry. So what is the volume of oxygen used up? The volume of oxygen used up in this case is 2.3 millimeter cube of oxygen that was being used up. In the second experiment, without soda lime or potassium hydroxide or sodium hydroxide, the liquid droplet did move to the left, but it only moved a total of, let's say, 2 millimeters. So why did it move a total of 2 millimeters? Because the one on the left moved 8 millimeters, the one on the right only moved 2 millimeters. The reason is because imagine if the liquid droplet moved 8 millimeters because it uses up oxygen, but because the carbon dioxide was being produced, it pushed it back over there by a total of 6 millimeters, which means the net movement is only 2 millimeters overall, by the way. Okay, so in this case, we can assume that this is the volume which I'm highlighting here. This is the volume of carbon dioxide that was being produced by the insect. So in this case, what's the volume of carbon dioxide? It will be pi r squared, r being 0.3 squared, times L, which is 6 millimeters. So the volume of carbon dioxide produced by the insect is 1.7 millimeter cube. Okay, so what's the respiratory quotient of the insect in this case? The respiratory quotient is 1.7 divided by 2.3, and it will give you 0.74. So we can assume that in this case, maybe for some reason, the insect at 32 degrees Celsius, because that's when the experiment was being done, is respiring, but it's not really breaking down carbohydrates, is it? Because the RQ is 0.74. So we can assume that in this case, the insects might be breaking down more lipids as a source of energy to produce ATP. These are how the experiments are usually done to determine the RQ value.